Hello everyone, I am Dr. Radioactivity. I welcome you in my YouTube channel. Today in this video, I am going to talk about radioactivity. Friends, I hope this video will be helpful to you. So let us start natural radioactivity. What is natural radioactivity? Natural radioactivity is the process of a spontaneous, without external means by itself, disintegrations of the nuclei of heavy elements with the emission of radiations. These are unstable nuclei found in nature. Natural radioactivity. The element whose nuclei spontaneously disintegrate are called radioactive elements. Examples of natural radioactivity are uranium gives thorium, thorium gives protactinium, radium gives thorium. After removing alpha, electrons and alpha pi. Now, natural radioactivity, all heavy elements above Z is equal to 82, where Z is atomic number, show the phenomenon of radioactivity. The emission of radiations changes the structure of the nucleus and transform the atom into a lighter atom. Now friends, the heavy elements are unstable, therefore they disintegrate to acquire a more stable state. Since radioactivity is practically unaffected by temperature, pressure and other conditions, we conclude that it is a nuclear property. Therefore, alpha beta particles and gamma rays are emitted from the nucleus. It may be noted that electrons revolving around the nucleus are not responsible for radioactivity. So artificial radioactivity is the process in which a stable nucleus is changed into an unstable nucleus by bombarding it with appropriate atomic projectiles like alpha, neutron and protons. You can see here aluminum and helium give the phosphorus nucleus, boron and helium give nitrogen nucleus, and nitrogen gives the carbon nucleus. So, the difference between natural and artificial radioactivity. The natural radioactivity is spontaneous, since in natural radioactivity, the nuclei of heavy atoms disintegrate on their own account, forming slightly lighter and more stable nuclei and emitting alpha, beta, gamma radiations. It is not spontaneous, since in it the nuclei of the atom have to be bombarded by fast moving particles like alpha, neutron, proton, neutrons. Natural radioactivity is uncontrolled and hence it cannot be slowed down or accelerated by any means. But artificial radioactivity can be controlled by controlling the speed of the bombarding particles used for bringing about the artificial radioactivity. So friends, units of radioactivity. The standard unit of radioactivity is Curie, and Curie is defined as the mass of radioactive element which produces 3.7 into 10 power 10 disintegration per second. So what is the equivalent dose? Is a dose equivalent या quantity representing the stochastic health effect of low level of ionizing radiations on the human body. It is derived from the physical quantity absorbed dose, but also take into account the biological effectiveness of the radiations, which is depend on the radiation's type and energy. So other common radiation units SI gray. To measure the absorbed dose, the amount of energy actually absorbed in some materials and is used for any type of radiations, and any material does not describe the biological effects of the different radiations. GY is equal to joule per kg, 1 joule of energy deposit in 1 kg of materials. Roentgen is used to measure the exposure, but only to describe for gamma and X-rays, only in air. R is equal to depositing in dry air enough energy to cause 2.5 into 10⁻⁴ coulombs per kg. Roentgen equivalent map. To derive equivalent dose, related the absorbed dose in human tissue to the effective biological damage of the radiation. See below. To derive equivalent dose, the absorbed dose in human tissue to the effective biological damage of the radiation. SV is equal to GY into Q, where Q quality factor, unit to the type of incident radiations. Becquerel. To measure a radioactivity, the quantity of radioactive material and that have one transformations, becquerel is equal to 1 transformation per second. There are 3.7 into 10⁻10 BQ in 1 curie. So detection and measurement of radioactivity. The radioactivity of the radioactive substance is detected and measured by instruments like Ziegler-Muller counter, Wilson-Cloud chamber, scintillation counters, and dosimeter. You can see GM counter, anode, ionized gas atom, ionizing radiations. Scintillation counters, you can see incident particles, luminous photons, secondary photoelectrons, scintillations, optical contact, light guard, photocathode, photoelectrons, light screen, high voltage divider and pulse amplifier, photomultiplier, data storage system, high voltage source, pulse discriminators, digital counter, multi-channel analyzer, or coincidence circuit. So dosimeter, you can see the unit 0.12 micro SV per hour. Types of radioactive rays. There are 3 types of radioactive rays, which are alpha, beta, gamma rays. Alpha represented by helium-2, an alpha particle is a helium nucleus whose mass number is 4 and nuclear charge is +2. Alpha particles decay. For proton-rich heavy nuclei, a possible mode of decay to a more stable is by alpha particle emission. Alpha decay has largest ionizing power, ability to ionize molecules and atoms due to largeness of alpha particles, has lower penetrating power, ability to penetrate matter, skin, even air, protect against alpha particle radiations. When a radioactive element emits an alpha particle, the mass number of the daughter element is decreased by 4 units and atomic number gets decreased by 2 units. You can see polonium converted into lead by removing of alpha particles. So alpha decay, you can see unstable atom Z and A, more stable atom A minus 4Z minus 2, and alpha particle. So radium redance formations removing alpha. So alpha decay X, you can see radium redancing. You can see here. You can see here. You can see here. You can see here. Now beta decay. A beta particles denoted by beta is a fast moving electron which is emitted from the nucleus of an atom undergoing radioactive decay. Beta decay occurs when a neutron changes into a proton and an electron. Many neutron-rich radioactive nuclides decay by changing a neutron in the parent nucleus into a proton and emitting an energetic electrons. Friends, many neutron-rich radioactive nuclei decay by changing a neutron in the parent nucleus into a proton and emitting an energetic electrons. You can see as a result of beta decay, the nucleus has one less neutron but one extra protons. The atomic number Z increased by 1 and the mass number A stayed the same. Many different names are applied to this decay process: electron decay, beta minus decay, negatron decay, negative electron decay, negative beta decay, or simply beta decay. You can see converted into polonium to styrene. You can see here polonium to redance, thorium to protactinium, tellurium to lead, bismuth to polonium, lead to bismuth. So comparison between a beta particles and electrons. Both the particles are negatively charged, which is equal to -1. When an atom loses an electrons, a cation of the same element is formed. On the other hand, when the nucleus loses a beta particle, a new neutral element is obtained. So gamma rays are not charged particles like alpha and beta particles. Gamma rays are electromagnetic radiation with high frequency. When atoms decay by emitting alpha or beta particle to form a new atom, the nuclei of the new atom formed may still have too much energy to be completely stable, and this excess energy is emitted as gamma rays. So gamma rays are electromagnetic wave photons emitted from the nucleus of an atom. Gamma decay very often in nucleus that undergo radioactive decay is left in an excited energy state. The nucleus can then undergo a second decay to a lower energy state by emitting photons, and photons emitted in that way is called gamma rays. Now absorption of gamma rays. Many nuclides emit gamma rays of more than one wavelength. If gamma rays of lambda are selected, their absorption is an exponential fraction of absorber thickness, that is I is equal to I naught E minus mu d. So I is equal to intensity transmitted by thickness of the absorber, I naught the intensity of gamma rays incident on the absorber, mu the linear absorption coefficient. You can see gamma rays passing through an absorbers. This is the absorptions. The absorption of gamma rays increases with atomic number of the materials of the absorbers. So friends, hope this video will be helpful to you. If you like this video, then subscribe my channel, and thanks for